Hello everyone, this is Rahul here. So we are at the placement preparation series of operating systems, and we almost completed two chapters: the overview of operating system and operating system structures, the computer system structures. Like we talked a lot about process, all those things, but we have not get much things which is deeper into it, right? So today we're gonna get into chapter number three, which is processes. So it's a very huge concept, guys. Why? Because we need to know a lot and lot about processes. Okay. Why? Because in terms of operating system, when you're learning about operating system, you're supposed to know what process is all about, how we are gonna schedule your process, what are the operations which is being performed on processes, right? And today in this section we'll be seeing what is all process is all about, how we are going to schedule the process, and what are all the operations we are going to held on the processes. And there is somewhat things you're supposed to know, which is nothing but your inter-process communication, the communication which happens inside the process itself, examples of IPC systems and communication in client server system. We'll talk about this in the next section of your next section of this video, right? We're going to talk about that in the next section. Today we'll cover about what process is all about, what is about scheduling, what are the operations which is being performed on the processes, right? Okay, let's talk about processes. Okay, so what is all about processes? So we know that operating system executes varieties of programs, right? Why? Because we already said that, yeah, and I'm still what I'm just repeating the definition of OS in such a way that it's going to be an intermediary for the user, which gives them access for accessing the computer hardware, where the OS is going to execute varieties of program to access the computer hardware, right? So where the OS is going to execute a varieties of program to access the computer hardware. So what are the varieties of program the operating system is going to be executed? So first thing is all about batch systems, that is nothing but jobs. And next is going to be time shared systems, one is nothing but user programs or tasks. These are nothing but your mnemonics, the naming categories what they have said. So mainly OS want to take care about jobs or user programs. Jobs are nothing but batch systems. Jobs are nothing but your batch systems, and user programs are nothing but the program which is given by us. It can also be a time shared system, right? And the textbook, Abraham Silberschatz textbook, will refer the terms job and process almost interchangeably. And what one case if you see job and another case if you see process, all the things are going to be same, right? So please don't take much consider about it. Now let's talk about what is all about a processes. Yes, I got a doubt. So, what is all about process? We are talking about a process. We talked about the operating system is going to execute a varieties of programs, which is going to be jobs, and we can able to say them as user programs or tasks. What actually process is all about? What is actually a process? Let's dig much deeper into it. Let's have a process. Let's have a program. We already learned about what is a program. The program is nothing but a set of instructions which is used to solve a particular problem. Am I right? But I don't know that whether the program is under execution or not. We say that if the program is under execution, then that program is going to be called as a process. Very simple, guys. When a program is under execution, then that program is going to be called as the process. Okay, and the process execution must progress in sequential fashion, that is one after the another. It should be progressing in other cases one after the other, right? So please try to cover those things in a much equal way. What are the parts, what are the multiple parts of the process? As I said, process is going to be a program which is under execution. What are the multiple parts of the program? The first thing, multiple parts of the process, first thing is going to be the code, where the program code, which is also called as text sections. I'm just for your understanding, I'm saying you are supposed to know about what is process all about. Process is a program under execution. And we already know about the PC register, the program counter, which takes about the number of steps which is needed, as well as it also has the address of the next instruction to be executed, right? And you also know about stack, which contains the temporary data. You can also store all of your parameters inside the stack, as we already talked about parameter passing in the last section of your video. Like we talked about, we've used stack to store the function parameters. We can also store the return addresses. We can also store the local variables so that it can be stored in the data structure called as last in first out. Okay, which has been pushed into the stack as last, is being popped out from the stack as first. And data section which contains global variable, which contains about the data which is needed for your program process execution. And finally, heap containing memory dynamically allocated during runtime. Clear? So now, so far we learned about what is a process. I'm not done yet. We are going to talk about a process. The process is nothing but the program under execution. I'm just repeating for your understanding. Program under execution, and it can be sequential. And very important thing, the parts of the program include the test section, stack, and your program counter, heap, etc. Clear? Just for your understanding. Okay, now let's talk about what is a so we already know about program. We had just seen in the last slide that program is going to be the set of instructions, and the program which is under execution, we term that thing as the process. Am I right? Yes, we did all those things in the last slide itself. Now, program is a, we declare program as passive entity. We declare program as passive entity and process as the active entity. Just get to know about it, guys. Why? Because as I said that process is under execution, so it should be active so that it going to execute it. So we can able to say that entity as an active entity, right? Yes. So program is a set of instructions. We can't able to say whether the program is under execution or not. So it still states that the passive entity. So we are going to term the program as the passive entity. So what happens? So we can able to say program is going to be an executable file. Am I right or wrong? Yes, program is going to be an executable file. Why? Because it's going to have set of instructions to execute to accomplish a particular task. So we'll make sure to execute those things to convert the program into a process. So what we need to do to convert the program into a process, we are supposed to load this executable file into the memory. Okay, we are supposed to load the executable file into the memory. Once we loaded the executable file into the memory, then we can able to say the passive entity, which is nothing but the program, has been converted into an active entity called as process. Okay, and execution of program started via your mouse clicks or command and entry of names, etc., etc. We do know about that. So for compiling a C program, first we'll write. So you guys know, right? So we know while we are writing a C program in our normal GCC compiler, right? What happens? It's very simple thing. We'll start creating a file called as sample.c. We'll write the code. We'll save the code with the extension .c or .cpp, .c, .cpp, .c++ for any of your .cpp for your C++ code, .c for your C code, right? Then you'll start compiling it and you start running it. So there are a lot of series of steps you do, right, for executing a current program. So for this program, when it comes into execution, we can able to say that's going to be a process. So for executing a process, you need to know some GUI clicks and some of the command lines for a compilation. For running, you need to know some command line entry or some commands to run the C code. Okay, right. So this is going to be the process in memory, guys. Let's see, we talked about it. What are the parts we seen about text code, which contains the code, and we talked about stack, which contains the function parameters, and we also talked about return addresses, local variables, and we also talked about the data part, which contains the global variables. We said about that. And we also have heap for immediate access, and heap is also for dynamic memory allocation. We already talked about that. Heap is already for dynamic memory allocation. And we also have another thing called as data, right? We also talked about data, right? Program counter, yes, the very important thing, the program counter, which finds or which counts the number of lines of codes, or it also finds the next address where the next instruction to be executed. This is how in memory, the process will be there. So first you'll have a stack. This is from 0 to max, which represents the total address taken by the process, the total space taken by the process, 0 to max. So it can't able to take after max. Greater than max, it can't able to, sorry, it can't able to take greater than max, right? So it should be less than max. And you have a stack, you have a heap for dynamic memory allocation, for stack for function declaration, and like for storing your function parameters, local variables, heap for your dynamic memory allocation, the data which is needed, the text code which is needed, and this is for your global variables or program counters. Any other registers what you have to use, you can use the space, right? So this is how the process has been seen inside the memory. Clear? Clear enough? Okay. So now, so far we learned about what is a process all about. A program under execution is going to be called as process. Then we also talked about program as a passive entity, process is an active entity. What are the things to be required for a process? We talked about how the process is going to be is seen in terms of seen in memory, where we allocated the space from 0 to max, and heap, stack, global variables, data, text, program counters, each and everything we have seen. Now we are going to see about the states of the process. We said that when a program is going to be changed into a process, am I right or wrong? Yes. Why? Because program is a passive entity, process is an active entity. So we are going to change the program to a process by loading the executable file to the memory. So then the process will start executed, right? Am I right? Why? Because when the program and execution, there is going to be called as process. When the process starts executing, it will change the state. Why? Because the process will not remain at one single state itself. It will start changing its state. So now we're going to see about what are all the state it is going to changes. We are supposed to know those things. We need to know in advance, so that once we get to know about how the process get executed and how the change of the states can be changed, then it's going to be very simple for us. What are those things? Let's see about that. Let me change the color. Okay. First thing is new. New is nothing but the process which is being created. New is nothing but the process being created, which is a new process. Second one, running, the process which is currently running inside the memory or inside the CPU. Waiting, waiting state is nothing but we already have a process running inside a CPU. Let's take it as P1. P2 is waiting for CPU unless until P1 gets completed. So it has to wait until P1 gets completed. So P2 is under waiting state. Fourth one, ready. The process is waiting to be assigned to a processor. Now P2 is ready. We are supposed to assign the processor to get executed. Finally, point number 5, the fifth state is going to be terminated. Once the process gets completed, once the process P1 gets completed, we are supposed to terminate the pre-one. So it gets under the state called as terminated state. So there are 5 different states of the process: new, running, waiting, ready, as well as terminated. So let's see a diagram for the process states. Okay, let's get into the part. Now I'm creating a new process. Let's call it as process number P1. Now P1 gets ready for execution. Am I right? Once the process gets created, we are supposed to get ready the process. So P1 gets ready, and P1 has a state called as ready. Now what we are supposed to do after ready state, we are supposed to either move to a running state or waiting state. Why? Because when the CPU is free, then we can move the process P1 from the ready state to the running state. But if not so, if the CPU, if the processor is not what can I say, not ready, some of the other process has been currently executing inside the processor, then P1 has to be in waiting state. So we are supposed to use a scheduler dispatch in such a way that we are supposed to move the process P1 from the ready state to the running state. If not so, or we need any other things to be done, or IO or even completion stage is there, we are supposed to move from what we are supposed to do. We are supposed to move from ready state to the waiting state. But actually, what happens is nothing but in some of the case we might have the process comes directly from a ready state to the waiting state. But at one single case, from the running state, it can come to the waiting state. As I said in the beginning, in the next from the first two classes about what we are learning about the overview, we said that if any IO interrupt or any IO device is needed for the process, then it has to wait until the IO device has been attached to the process P1. So what happens from the running state, the process comes to the waiting state unless until the IO device has been attached to it. Yes, now after IO device has been attached or the event has been completed, then from the waiting state, the process P1 goes to the ready state. Why? Because we can't able to what can I say, allocate the CPU unless until the IO devices, the what can I say, the allocation of IO devices for process P1 should be completed, right? It can, the C processor can execute other process like P2, P3, which is in the waiting state, right? It can be done. So then after executing, then after the CPU is free, then the P1 gets executed. Am I right or wrong? Am I right or wrong? Yes. But in some of the cases, what happens, right? Let me change the color of the pen to make sure to give you an overview. From the running state, it can come to the ready state. What happens here? From the running state, come to the ready state in such a way that there is some interrupt has been happened, where we need to use an ISR from the interrupt vector to handle this thing, so that from the running state, I am moving the process P1 to the ready state, so that after handling the interrupts, then it moves to the running state. Clear? I've said two different cases. Ready to waiting is one case, running to waiting to the next case, waiting to ready to the next as a third case, right? To make sure to understand you a much better view about how the states has been transisted. Then after running all those things are done. Yes, I have completed process P1. Then the process gets terminated. Clear about how the process states happen, how far the process has been over of the process is being make sure that the states of the process has been transited. Okay, let's talk about the PCB, the process control block. So give me so far we learned about what is process, and we also talked about the states of the process. Now let's see about the process control block, which is being abbreviated as PCB. Okay, we said that for each and every process we have allocated some of the things, right? We talked about stack, we talked about heap, text block, data, program counter, etc. So there is somewhat an information associated with each and every process. Why? Because we're going to execute it to make sure to get some information from the process. Am I right? So after executing the process, we are supposed to get any output, which is going to be the information what we are supposed to get from this thing. Am I right? So we are supposed to get information in such a way that as that kind of information has been associated with each and every process. That is going to be called as task control block. Okay, the information which is being attached to the process, running process, is called as task control block, called as task control block. So we said that there are lots and lots of things we talked about it. Let's get into it. So in terms of PCB, what are all the things where the program process control block contains? We're supposed to know about it. The first thing, it has the state of the process. Why? Because each and every process will have the process control block, where the process control block will say about the process information, some of the information. The kind of information can be the state of the process, the kind of information can be the process number, program counter, registers which has been associated, scheduling information, action, etc. The first foremost information what we're going to see here is process state, the state of the process. Let's take process P1, right? The state of the process, whether it is in the running state, ready state, waiting state, terminated state. So it can be of any states. We are supposed to know about the state of the process. Second thing, the program counter. The program counter will find the location of the instruction which is to be executed next, as I said already. So we are supposed to know about when the process being executed, it is going to be executing instructions sequentially. So once the instruction I1 has been completed, the program counter will have the location of the instruction I2 where it is to be executed. Clear? Yes. Then we also have the CPU registers which has been associated, and finally fourth one, we have CPU scheduling information. What are the priorities which has been involved inside the process? As I said, we are going to follow lots of algorithms for this thing, Right now we are not going to see the algorithm, but please try to understand that. First of all, why algorithm is being used, right? The priorities, we are supposed to maintain the priorities for the processes. If we're going to have mutual mutex locks and kind of like, we are going to learn about that mutex locks and scheduling queue pointers. And we also know it also, PCB also contains about the memory management information, the memory which has been allocated. We already talked about it. So from 0 to max, for each and every process we are going to allocate, for 0 to max we're going to allocate memory, which contains heap, which contains stack, which contains program counter, which contains your data, text, global variable, etc, etc. It is going to have it. Then it will also have the accounting information and the IO status information. So these informations are present inside the program or the process control block. Clear, guys? Okay, for each and every process there is some kind of information. Those informations are stored inside or contain the stored inside a block called as process control block. Clear? Okay, so now let's see how the CPU switches from process to process. Let's take process P0 and switches to process P1. Okay, let's see. We have process called P0, we are called process as P1 operating system. I'm going to execute my P0 as my first process. Why? Because the priority for process P is higher. Okay, based on the scheduling algorithm, I'm going to schedule process P0 first rather than P1. On what basis? There are different bases where the process, some of the process can be scheduled, some of process can be scheduled based on the first come first serve, based on the priority, based on the round robin scheduling. We have lots and lots of scheduling algorithm. We are going to learn a lot about that. We are going to mention, we're going to learn about each and everything what we're going to do those things, right? Okay, let's give you an instance. So P0 is going to be executed. So let me rub this so then make sure that I'm going to execute it under one point of execution. Like what happens at one point of execution, let's say at time t. Okay, let's say at time t, what happened is nothing but P0 got an interrupt or a system call. What happens? P0 got an instance from the person got a system call, so that interrupt in such a way that P0 has to it can be any kind of interrupt. It can be an hardware interrupt, can be a software interrupt, it can be any kind of interrupt, IO interrupt, etc. So we are supposed to state the save. That means we are supposed to save the state of PCB0. Am I right? Yes. Why? Because the state has been changed from executing that, from the running state to a ready state. Am I right? So make sure that it has to wait until the P0 gets its where we are supposed to run the ISR for the P0. Then we have to what can I say, invoke it for. But that for that particular point of time, why can't we make sure that, why can't we start running our PCB1? So after saving the state into PCB0, we are supposed to take the PCB1 and we are supposed to reload the state from PCB1 and start executing the PCB1 at time t is equal to t1. At time t is equal to t0, P0 got an interrupt. At time t is equal to t1, I start executing the process PCB1. Am I right or wrong? Then at point at time t is equal to t2, what happens? Nothing but p2 times t2, process p1 got an interrupt. So what happened? I am supposed to change my PCB1. I have supposed to change the state of PCB1. I have done it. And so since at this point of time, at this particular point of time, from t1 to t2, the ISR for p0 has been done. From the interrupt vector, I have used the interrupt service routine to resolve the interrupts. Now P0 is free. I have free from the interrupts. All the things has been done. So I have to reload the state from PCB0 and start executing. So this is how the CPU will switch from process to process unless until one entire process gets executed entirely. It can also have some partial execution when there is any interrupts, so that the processor, the operating system, will not be idle for a particular point of time. When we need to make sure to switch the process from process, make sure to have some high throughput. Clear? How CPU switches from process to process? Clear? Okay. Now We learned a lot about it. We learned a lot about processes. Now, we already said that process is gonna be a program under execution. Am I right? I'm just I what can I say? Repeating the definition so that we can able to understand from the what from understand what the what we have learned from the previous slides. Program under execution, and we know that a process is a single thread of execution. Am I right? Why? Because we're gonna run only one single process. It's gonna be having only single threads. But for fact, in fact, whether operating system is going to have only one single thread of execution? No. Why? Because we can have multiple program counters per process. Okay, one single process can have multiple program counters where multiple program counters have lots and lots of threads. So we are supposed to have those threads controlled too. Clear? We are supposed to have next control the controls through multiple location can execute at once. Why? Because we have thread number one, thread number two at memory location M1, here at M2, here at M3. Each and every thread will start executing at particular parallelly, right? Concurrently start executing. So we are supposed to handle those multiple program counters which has been executed at memory M1, M2, M3. So we are supposed to have a thread so that we are making able to show that we are supposed to handle those things. So must then have storage of thread details, multiple program counters in PCB2. Just an overview. We're gonna learn a lot about threads in the next chapter too. Okay, so as I said, we're going to learn about Linux over here. So how the process representation is given in terms of Linux. Let's give you an overview, right? I'm created a structure which is called as task struct. Okay, why? Because you know a structure is a data type inside C which where it can store multiple data types. So first of all, I'm going to have PID, which is a process identifier. As I said, we're going to have a process identifier. Either it is P0 or P1. We need to identify. We need to give the process and the state of the process and the time slice, the scheduling information. The time slice is very, very important, guys. We will come to know about what time slice is all about. You need to know about those things while we are getting to know about the scheduling of process into an operating system. Then we need to know about the parent process, children process, the list of open files inside the process, and the memory address of the process. So these are the things which has been represented for the process. As we already know, each of these things will be there for a PCB block. So while we are creating a process representation in the next, we are supposed to give all those information. Clear? Okay. Let's come to our final topic of today's session, which is nothing but scheduling of process. So far so good. We learned about what process is all about, stage of the process control block. We also learned about how CPU switches from one process to another. We also talked about threads, where when multiple program controls are executed at once. So far, so good, we have learned a lot about it. But we're supposed to know which process should be scheduled inside the operating system. Which process should have the priority towards in which that process P0 gets more priority than P1 so that P0 guards start executing first. We are supposed to know those things in advance. Okay, maximize CPU use, quickly switch processes onto CPU for time sharing. Am I right or wrong? So far, what we have done here for time sharing, what I have done, we don't want to make the operating system idle for this particular point of time. We don't want to make the operating system idle for this particular point of time. What we have done, we have made the operating system from switch from process P0 to P1 and vice versa when the process P0 or P1 at any interrupt at a particular point of time at time t0, t0 and t2. Clear? Okay. So we are supposed to make sure to switch the process from CPU so that it has maximum throughput, as well as we can also, what can I say, share, spare, what can I say, save some time, and we can also share the time which is being allocated for the CPU. So who's gonna do those things? The process scheduler selects among available process for the next execution of CPU. As I said, P0 got an interrupt at T0, so that inside PCB0 I've changed the state. Now I'm supposed to find the next process which is on the ready state so that I can start executing, right? Who finds, who selects the process? Let's have P1, P2, P3, P4. There are lots and four to five processes. Who's gonna select the process for the next execution of the CPU. The one is nothing but the process scheduler. The one is nothing but your process scheduler, which finds which selects the process so that it gets started executing inside the CPU. Okay, how now you can get a question. Now so far process scheduler is going to select which process is going to be executed in the CPU, when is there any interrupts has been happened for the running PC or running process, or the process gets terminated. How how the process scheduler is gonna select the process? Let's see. So it maintains the scheduling queues for the process. It's a very, very important thing, guys. Let me change the color of the pen here. So it is gonna maintain the scheduling queues of the process. What are those things? It's gonna maintain three different scheduling queues. Let me rub this to write here. Okay, it's gonna maintain three queues. One is all about job queue. One is all about ready queue. One is all about device queue. Might you might know from the name itself. What is job queue? As I said, job processes, which is being interchangeably the set of all processes in the system, which is being arranged inside a queue. Let's take P1, P2, P3, P4, set of all process arranged in a queue. Am I right? Set of all process arranged in a queue. Then ready queue. Ready queue maintains that we are supposed to know what are the process residing in the main memory, ready and waiting to execute. We are supposed to know what are the process which has been ready, which has been waiting to execute. So we'll arrange that inside the queue. Let's stack P1 and P2, which has been ready and starting to waiting to execute. The device queues. Device queue is nothing but a set of processes. So we are device queues is nothing but it has another queue where the set of processes being arranged inside this, where these processes are waiting for the IO devices. Okay, and the process might migrate from one queue to the other queue. Okay, what are the scheduling queues? Job queues, which finds the listed set of all processes in the system. Ready queues, which contain all the processes which are ready and ready for execution. And finally, it's gonna be my device queue. Device queue consists of the process which is waiting for your IO devices. Clear about the process? Clear about the scheduling queues, which has been maintained by the process scheduler. Okay, now let's talk about ready queue and various IO devices queue. Let's give you an example. Okay, just you can able to understand this from this thing. Okay, I'm gonna have a queue header which contains the head and tail. Okay, which points. So this is going to be my ready queue, guys. Ready queue consists of process P7 and P2 in such a way that P7 and P2 are ready to execute. Okay, so the head of the queue points to PCB7, and the PCB7 points to PCB2, and it points to the ground. Clear? And what disk queues? So the device queues. Device queues nothing but PCB3, that means the process 3, process 14, and process 6. All those things are waiting for your devices. So the head of things is pointing towards the things, and the tail is pointing toward the end of the thing, and finally to the ground. And terminal queue contains the list of process which has been terminated. So 5 is being terminated, process 5 is being terminated, so it's being pointed directly to it. Clear? Clear up to this? Okay, right. So how the process scheduling can be represented? A very important question, guys. Yeah, even though if you write your examinations on operating system, I think so this question will be an very important question. How the scheduling process has been represented? One of the important diagram which has been used to represent your process scheduling, a kind of scheduling queues. Your lots of we have talked about three queues, right? Job queues, ready queues, and device queues. What is the diagram which is going to represent that? The diagram which is being used to represent queues and resources and flows are called as queuing diagram. Okay, it is called as queuing diagram. What is all about? Let's check. Let's take a process going to get into the ready queue, and after ready queue it is going to get into the CPU. After execution it is going to go for it. Okay, if it is going to be executed successfully, it is going to be into the terminated stage. If not so, If there is any IO request, it goes into the IO queue. After that IO, then it goes to the ready queue one more time. And if the time slice has been expired, then it is moved to the ready queue. Am I right? We have talked about, I'm not said about what time slice is actually it is. While we are seeing scheduling algorithms, we might know about what time slice is. And the child is being forked. Child is being terminated, and then we are supposed to execute the child, then we are supposed to move to a ready queue. And we are process P0 has been interrupted, then interrupt occurs after ISR from the interrupt vector, then moves to the ready queue. Can be of any things. Okay, there is possibility, there is can be a possibility number one, possibility number two, possibility number three, possibility number four, possibility number five. How far the queue process can be represented, how far the process scheduling of the process can be represented. So this is how the scheduling of the process can be represented through our queuing diagram. Clear? Okay, now schedulers, we talked about schedulers, am I right? We talked about schedulers. And okay, we'll talk. Okay, okay, fine. Sorry, we do have some things to do. Schedulers, we talked about schedulers. Schedulers are the one which is going to select the process when the CPU is under the idle stage, or some of the process has been waited for, some of the process has got some interruption, then we have to wait. We don't want to wait the system. We don't want to make the system make the process idle, so that scheduler will start selecting the process which has been executed and allocates the CPU. So there are two types of scheduler, guys. One is all about short time scheduler, another one is long term scheduler. Sorry, short term scheduler and long term scheduler. Short-term scheduler can be represented, can be termed as CPU scheduler, and long-term scheduler can be represented as a job scheduler. What is all about short-term scheduler? Why it is being given in terms of short? Why it is being given in terms of long? Okay, let's see. Short-term scheduler selects which process should be executed next and allocate CPU. Yes, I do know about it. And sometimes the only scheduler in a system. Short-term scheduler is invoked frequently. Milliseconds must be fast. Okay, why? Because the short term scheduler runs. Why the term short term is being given is nothing but it runs in terms of milliseconds. Okay, so that it can be executed frequently inside the CPU. And at some other cases we can able to say the short term scheduler is one of the only scheduler which is available inside our CPU. Only scheduler which is available inside our CPU. Then what is going to be a long-term scheduler? Long-term scheduler can be also be termed as job scheduler, which selects which process should be brought into the ready queue. Okay, ready queue. We are supposed to make sure that we are supposed to get the process to the ready queue, then from the ready queue to the what can I say, running queue. Okay, long-term scheduler is invoked infrequently. Why? Because the time needed for long-term scheduler is going to be seconds and minutes, so it might be slow. And long-term scheduler controls the degree of multi-programming. Clear? So far clear about how schedulers is all about long short-term scheduler and long-term scheduler. And so far we learned about process. Let's see about some description about the process. I don't think that this description will work for you, but I'm saying those things. One is IO bound process, another one is CPU bound process. What is IO bound? IO bound process nothing but the process for a process which spends more of its execution on the IO devices than the computation, many short CPU bursts. Okay, what is CPU bound process? Nothing but the process may focus only on the CPU rather than concentrating on IO, starts to spends more of time on computation, so that very long CPU might burst. Clear? This is all about the short description of the process. Can you know about what scheduler is all about? Okay, now addition of medium term scheduling. So far we learned only two types of scheduler. One is going to be short term, long term. There is one more thing called as medium term scheduler. Okay, why? Because we learned in the previous thing that what is long term scheduling is. Long term scheduling is nothing but it invokes the degree of multi-programming. Am I right? Yes. Degree of multi-programming, because multiple programs can be executed at one particular point of time. Am I right? Degree of multiple programming is. If you want to reduce the degree of multi-programming to a particular extent, then you can use a medium-term programming. sorry, medium term scheduler. I'm sorry, guys. You can use a medium term scheduler. Just get to know about this. If you want a lot about it, you can just see the diagram. Why? Because so far so go, most of the operating system point of view, they know only two types of scheduler. One is long term and short term. But most of the things they won't know about what medium term scheduler is all about. Just to know about that, it is added to degree to reduce the degree of your multiple programming and remove the process from the memory, stores on take, bring back to the disk to continue execution. It contains the swapping thing, but we are going to talk about swapping a lot in memory management topic right now. Just get to know about how the medium term scheduling is going to happen. We are going to remove the process from the memory, store in the disk, bring back to the disk to continue execution. A kind of swapping is going to happen, right? We'll talk about that in the memory management in detail. Okay, you know about how multitasking in mobile system happens, because we are what can I say, for one say for 1 minute we are opening a phone for more than 10 times and having multiple programs. So why? Because in our in what can I say, we have single program process or multiple background process which is running behind. We'll add that into our list and we'll scroll it up and we'll start doing what are the recent activities what we have so open so far and what are the things which is happening concurrently. So we are working in the multitasking in terms of mobile system, right? So you guys know about it, right? Okay. And I don't want to talk about context switch right now. Why? Because when we are talking about memory management, we'll come back to the context switch. Why? Because this is what we need. Okay, now let's talk about the final topic, right? Why? Because that's not the final topic, we already know about it. Why? Because why I've said that as a final topic is nothing but when we are talking about scheduling part in your process, we are supposed to know what are the operations which is being processed performed in the process. What are the operations which is being performed in the process? The first thing, when the process is there, let's talk about process P1 is there. First thing is process P1 should be started. Am I right? Started in such a way that first of all the process should be created. So this one for one operation we are supposed to perform. The process should be created. Then then the process should be executed. Then then the second thing we are supposed to terminate the process. We are supposed to terminate the process and so on as detailed next, right? What we're going to see, first one we are supposed to create the process, second thing we are supposed to terminate the process, and what are the things we are supposed to do. Okay, we know that we already talk about while we are creating a process, we created the parent process and child process, right? The parent is the one which has the responsibility to create the child process, and you can see a beautiful tree of process in the next. Why? Because this is going to be my parent node or a root node, where the root node has the capability to create login id, this process, this process, and this process. And login process to create the bash process, the bash process to create the process called as ps and emacs. K thread process should create the k helper and pdf flush, and sshd should create another process called as sshd and tcs. So the parent process should have the capability to create the child process, guys. Okay, and each and every process, as I said, it should have a program id, pid, which is nothing but the identifier, and it will work under the tree data structure. How far you guys know about the tree data structure and data structures topic, it will work in the same case. Now, how the process, so we are supposed to know about process creation, process termination. These are the two important steps, two operations of the process. How the process being created, the first thing and foremost thing, we are process creation is nothing but with the help of program id, the parent process should create the child process. So far we know about it. Now, fork. Fork is nothing but a system call. Why? Because we learned about what system call is all about. Am I right? What is system call and what is system programs? If you guys remember, yes, we talked a lot about what system call is and system program is all about. Call is nothing but the program which is needed for the operating system for the execution. The program under which the operating system services can be executed is going to be called a system call, and system call should need an infrastructure, need an environment. So it has a system program so that it can have an environment to start executing the program. This is nothing but the system call. So the fork is the system call which creates a new process. Okay, it's the system call which creates a new process. It can be a parent node and can be a child. So we know about it. It can be a parent to any one of the process, or it can be a child of any one of the process. Execute is the system call which executes the process. Exit is a system call where it exists from the process. Okay, so far, like if fork, I've created a process called as P1. I create a new process. If it is going to be a parent process, then it is supposed to wait. Okay, supposed to wait. If it's going to be a child process, then I'll execute it. I'll add it to the child to any one of the parent, and I'll exit it. This is how the process creation is going to happen. Okay, so what are the address space we are supposed to give? The address space we are supposed to give is nothing but the child duplicate of a parent, and child is a program loaded into it. So this is how it's going to be the C program for forking a separate process. And using this header file, sorry, using these three header files, you can fork the process ID. Fork will create a process ID. If the process ID is less than 0, we can say that fork is being created, fork has been failed. If process ID is equal to 0, nothing but my ls is null. Else we can able to say wait of null. Yeah, I'm gonna wait for a particular point of time. Then I can able to say the child has been created successfully. Okay, so this is what we can able to use with the help of Windows API, right? With the windows.h as header file, we can able to create a process. Okay, now so far we learned about one single operation of the process, which is process creation using fork system call and execute system call. Then how we are gonna terminate the process. At the last execution of the process, we are supposed to terminate the process using our exit system call. Using the exit system call, we are supposed to ask the operating system to delete it using the exit system call. And we are supposed, if we want to return the status data from the child to parent via wait, we can also do it. Or else, we can able to delete, like we can ask the operating system to delete the execution using exit system call. There is one more system call is there, which is called as abort. Okay, abort, there is something difference about abort and exit. Exit system call happens when the process gets executed fully, completely. Then the operating system should delete the process called as P1. But abort is not like that. At one particular point of time, at time T1, I'm gonna abort the process P1 so that the entire process not get executed fully. What are the reasons to doing this? What are the reasons we are supposed to abort the system call? Abort the process. The first thing is all about the child has exceeded his allocated resources. Point number one, it can have those things. Second point, task assigned to the child is no longer required. We don't, so at time T, it has completed its entire process. I don't want to push it to the entire end of completion, right? Entire end of completion, I don't want to push it to it. And the parent is existing in the operating system does not allow a child to continue if the parent terminates. So if the parent is being terminated, we don't want to make sure the child is being present inside the particular system call, particular tree. So we don't want to make sure to have the system child's process to be executed. So we'll abort the thing. Clear about the process termination process, about an exit. Okay, this is what is new for me too. Why? Because I've learned this new from my from this book. Why? Because some operating systems do not allow the child to exist if the parent has been terminated. So if the process terminates, then all its children must also be terminated. The very important thing, if your parent or if your process gets terminated, then all of your child process should also be terminated. In some other case, we can say in terms of tree data structure, if I remove that particular node, I can make my child as the tree node based on the case what we can do with the help of other algorithms what we have. But here is not the case. You are not supposed to use the tree data structure over here. If the parent process gets terminated, then all the child must also be terminated. Okay, and we also follow one important termination called as cascading termination. If the parent is not only the parent, it is going to be a grandparent, then the child and the grandchildren of the particular grandparent is also being deleted entirely. Not only the immediate parent or immediate child, the entire family has been, what can I say, entire family has been deleted. It should be terminated. Clear? Clear. So far we are so far so good in terms of process termination. Okay. So the parent process may wait for the termination of the child process by using the wait system call. Why? Because We can't able to direct, we can't, so we are if we are supposed to check that, we are supposed to do that, we are supposed to delete the parent process. So first of all we have to delete all the child process, so the child process which is available. So what we are supposed to do, we are supposed to wait until all the child process has been terminated successfully. What we do, so we'll make sure to use PID is equal to wait of that status. Once the status has been true, then we can able to say that the wait has been completed and the PID can be terminated successfully, right? We are supposed to wait until all the child process being executed. If what happens, so let's give some things over here. If no parent is waiting, did not invoke wait, process is an zombie, right? It is going to be a zombie. And if parent terminated without invoking wait, then the process is an orphan. Okay, if the process terminated without invoking wait, let me give you an instance. If I'm going to have parent P1, P2, P3, P4, like I'm having like this. If the parent process P1 terminated without invoking wait in such a way that all the children has been terminated, then I can able to say the parent P, then the process is going to be orphan. Orphan in such a case that it does not have any parent or does not have anything, does not have any child. Okay, why? Because it is not the convention that P1 should be deleted first when we have an architecture like this. If the process P1 does not invoke any wait process, then we are going to say that the process P1 is not going to have any parent or child. So we can able to say process P1 is going to be an orphan. Clear? And if no parent is waiting, did not invoke wait, then the process is called as zombie. Clear? Clear about process termination? Okay. The multi-process architecture, which happens in the Chrome, we already know that. While we are saying that, while we are using our Google Chrome browser, we'll not end up with one single what may I say tab. We'll have multiple tabs. Okay. Those multiple tabs, each and every tab represents a separate process. Where those all the separate process runs parallelly. Clear? This is one of the simple example of your multi-process architecture. Clear, guys? Okay, so far the section 1 has been completed. We talked about what process is all about. We talked about the states of the process. First of all, we talked about what program is and how the program can be converted into a process. We talked about the states of the process. We talked about how the CPU switches from one process P0 to P1, and we talked about scheduling processes, operations of the process, which is nothing but the creation and the termination with the help of fork system call and execute system call, and termination using abort and exit system call. Clear? Clear? Okay. In the next video, we'll start discussing about the inter-process communication and other things which is needed for your process thing, for the chapter, for the chapter 3 called chapter 3 process. Okay. Thank you for listening. So we'll be catching you with the next session for inter-process communication, and by the next section we'll complete the unit number 3, which is called as processes. So I'll ping all those first entire three videos, which consists inside the placement preparation operating system over the operating system playlist in the top. So feel free to use those things for your first two units clarification. Then might get into an overview, and you can start parallelly with me. So we'll be seeing you with the next video with the inter-process communication. So subscribe for the channel so that you get more information about how the placement series has been going throughout in this particular year. So we'll be putting lots and lots of videos covering our computer programming fundamentals, DBMS, OS, computer networks, system designs, and we also started TCS NQT series. I'll be pushing my TCS NQT preparation series. I'm going to solve almost 75 problems within 20 days. Each and every problem I'll be solving five problems in one particular day. I'll share the playlist link in the description box below. Use those things and get placed with me. Thank you for watching. Thank you. Bye bye.